Hello, algebra students. This lesson is going to be on function notation. This is our second lesson in this unit on functions. And the goal of this lesson is to talk about a handy way to refer to and talk about a function. Like I said, this is building on what we learned about yesterday with functions. In yesterday's lesson, we introduced what a function is. We had the really main idea, the definition of a function. We said a function is a relationship where each input has only one output. And so we introduced that idea yesterday. The goal for today, like we said, is to learn a mathematical way to represent and write functions, and that's called function notation. Our warm-up is related to a question we had started yesterday. It was that problem we had looked at where a dog is tied to a post and the owner walks away. And we looked at 3 different graphs that described the distance the dog was from the post in feet and how much time in seconds had gone by since the owner left. I encourage you to pause the video now and try to work through this warm-up. Remember, there was 3 days that this had happened. And the question number 1 is talking about different information you can get from these graphs of these 3 days. Like I said, I encourage you to pause the video now and try these, and then click play when you have your answers to see how you did. All right, and you are back with some answers on this warm-up. For this, it's a lot of questions asking about different points on the graph. So for example, part A asked how far away was the dog from the post 60 seconds after the owner left. Well, on day 1, that's this first graph. If I go to 60 seconds and go up, I'm finding this point right here at 4 feet. So day 1, the dog was 4 feet away. On day 2, I'm going to do the same thing. I'm going to go over to 60 seconds and then up to the line. Oh, what do you know? It's also on 4 feet. And day 3, same thing. I'm going over to 60 seconds, going up to the blue line, and there's that point again. If you remember from yesterday, this was one of the things that we had said was going to be true for all 3 days. So it makes sense we're getting the same answer for each. In part B, the question was how far away was the dog from the post when the owner left? Now, unlike this first one I had a specific time I was given to look at. Here, we're talking about when the owner left. So we have to understand that when you're talking about when the owner left, that's going to be time 0. Another way to think of that is 0 seconds after the owner left, right when it happens. Similar to part A, it's going to be the same point for each. At 0 seconds, my line starts at right there between the 1 and the 2. That's going to be 1.5 feet. Same for the second one, between the 1 and the 2 at 1.5 feet. And also for day 3, 1.5 feet. That last question is asking about when the owner returned 160 seconds after he left. How far away was the dog from the post at that time? Looking at our graph, I'm going to go to the very end of my graph at 160 seconds. And just like all the others, I'm going to travel up to that red line and see where that line is. Now, this time when we're looking at those points, each of these points is going to be at a different number. So for my graph for day 1, it's not quite at the 4. So maybe something a little less than 4. It's not exact by any means on this graph. I'm going to guess it's at about 3.8 feet. But I think if you give me anything like 3.6, 3.7, 3.9, all of those would be good estimates. For day 2, that point's a lot easier to see. At 160 seconds, I can see my green line is right here at 4 feet. And then for that last day, 160 seconds, my blue line is down here. Again, it looks like it's about halfway between 0 and 1, so we're going to guess that's 0.5 feet. This warm-up here is really just about being able to read these graphs, looking at our input, which is time, and figuring out what the output or that distance would be from the graph. Now, there's one last question down here. Number 2 at the very bottom says, consider the statement, the dog was 2 feet away from the post after 80 seconds. Do you agree with that statement? I'm going to put those graphs on the screen again and see if you would agree with that statement. The dog was 2 feet away from the post after 80 seconds. Do you agree? When I've asked this question in person before, students say, well, when are we talking about? 80 seconds on the first day, our dog is right here, and that's not at 2 feet. 80 seconds on the second day, our dog is 4 feet away, but 80 seconds on the third day, our dog is at 2 feet. So the answer we get a lot from this question is, it depends. It depends which day are we talking about. On day 3, we're seeing, yeah, it is true there, but days 1 and 2, it's not. So notice when we're describing these graphs, we have to be super specific. You can't just say the dog was 2 feet away from the post after 80 seconds. We have to say on day 3, the dog was 2 feet away from the post after 80 seconds. After going through this problem, we're seeing there's a lot of language in these questions when we're describing these graphs. For example, in part C, we were saying that the owner returned 160 seconds after he left. The dog was 3.8 feet away from the post 160 seconds after the owner left on day 1. Or for part B, we're saying when the owner left, the dog was 1.5 feet away from the post on day 2. It's taking me a long time to say all of this. If you're taking notes, which I know you're taking notes, it's going to take you a long time to write all of that down. When it comes to describing these graphs, we have to be really specific, but when we're being really specific, it's taking a lot of language. Now remember, the goal of this lesson was to talk about a handy way to refer and talk about functions. We're seeing that all this language I have to use is not going to be the easiest way because it takes a lot of words to describe this. And so instead, we have an easier way to describe these different points on the graph, and that easier way is going to use function notation. So to show you how function notation works, I'm going to come down to this table here. And if you're taking notes, this table could be a great thing you could add to your notes. The first thing we're going to need to do for function notation is we're going to name these functions. So for this graph we've been working with, there was 3 different days we were talking about. We're going to name each of these graphs using a letter. So we've got down here in the description, we're calling day 1 function F, day 2 is going to be function G, and day 3 is going to be function H. That means anytime I'm talking about day 1, I'm going to be using the letter F to help me name it. Anytime I'm talking about day 2, that's G, and anytime I'm talking about day 3, that's going to be the letter H. The other thing we use with function notation is we're going to need that input. Input, remember from yesterday, is always going to be found on your x-axis. So right here, my input is my time in seconds. The output was our distance here on our y-axis. So when I'm using function notation, I need the name of each of these functions, that's the F, G, or H, and I'm going to need to know what input we're talking about. So for example, if I wanted to go back through those 3 problems we just talked about again using function notation, the first thing I would need is the name of the function. So for example, if I'm talking about day 1, I'm going to use the letter F, and I need the input. So if we're talking about the distance from the post 60 seconds after the owner left, that's 60 seconds, that time is my input. And so the way I combine this information is I put the name of my function first, that's my F, and then I put my input in parentheses. And so for this description here, that would be the 60 seconds. So I would put 60 right there. And so this right here is going to represent on day 1, the distance from the post 60 seconds after the owner left. Notice those 2 little things. The F and the 60 represents all of those words. When I see the letter F, it's letting me know we're talking about day 1. And when I see that 60, it lets me know we're talking about the distance from the post 60 seconds after the owner left. Day 2 and day 3 is going to be really similar. On day 2, I'm going to use the letter G now because function G represents day 2. So I would start with my G, but then inside those parentheses, because we're talking about the same input, we're talking about the same time, that would be the number 60. If you were talking about a different input, so for example, down here, when we're talking about 150 seconds after the owner left, if I still wanted to talk about day 2, I'm still using that letter G, but now I would just change my input. I would change what goes in parentheses to be the 150 seconds. So we get this right here. When I'm writing down something like this, now I know we've seen before when you have two things next to each other in parentheses like that, it can mean multiplication. This is not multiplication, and sometimes it's hard to get used to that change. When we're talking about functions, though, you're going to see this a lot, where you've got a letter in front and then you've got something in parentheses. Just know anytime we're talking about functions, this right here is what we call function notation. And I would read this out loud as G of 150. I'm putting that word of before I read the input. So that one there in blue would be F of 60 or G of 60. So notice I only filled in 3 of these boxes and there's still 6 empty ones. I bet you can guess what I'm going to ask you to do. I'm going to ask you to go ahead, pause this video now and see if you can fill in those empty boxes we haven't done yet. Come back and press play once you've got those answers. All right. If you're coming back now with some answers, for day 3, we do need the name of day 3. That is function H there. So if I finish that first row, F of 60 was the distance from the post 60 seconds after the owner left on day 1. G of 60 is the distance from the post 60 seconds after the owner left on day 2. For day 3, it's going to look real similar, except now I'm using the letter H. I would have H of 60 to represent the distance from the post 60 seconds after the owner left on day 3. If I wanted to finish this last row here, for day 3, I'm just going to use the letter H to let me know I'm talking about day 3, but the same input. And then similar for day 1, I'm going to use F for day 1, and then my input is again 150. That middle row, we've got the distance from the post when the owner left. Remember, I need a number here. If we're talking about the owner left, what time is that at? What would my input be? Well, my input would be 0. That means we're talking about 0 seconds. So for day 1, we would have F of 0. For day 2, I would have G of 0. And then for day 3, I have H of 0. So we've got a bunch of different examples here. This was us taking this description and coming up with function notation, but the opposite could also work. I could give you something like F of 15, and now we know 2 things. The F tells me I'm talking about day 1, and the 15 tells me I'm talking about 15 seconds after the owner left. And so that is going to be similar to the second. Oh my gosh, I used the exact problem. F of 15, we said, would tell me that in that situation, we're talking about on day 1, the distance from the post 15 seconds after the owner left. Again, I want to point out how great function notation is. Those 2 little things right there are representing this entire phrase. So similar to what we did for part A, you've got parts B and C that you're going to try, just like we did here in red. See if you can come up with a phrase or a sentence describing what those 2 things represent. Go ahead, pause the video and try those now. Right, for part B, the G is what I see first, and G lets me know we're talking about day 2. So I could start my phrase with on day 2, And then the 48 there is my input. That means we're talking about 48 seconds. So I could say G of 48 is going to represent on day 2 the distance from the post 48 seconds after the owner left. I think the last one could be the most challenging because notice we don't have a number. We don't have an input. I'm going to start the same way though. H tells me we're talking about on day 3. And the T just tells me we're not talking about a specific time. So we could say the distance from the post T seconds after the owner left. Means I'm talking about just some random time. We're not sure what time. But this whole phrase would represent on day 3, whatever that distance is at that specific time. Now, the last part of function notation is we can combine what we've been doing with equations. So, for example, I could write the equation g of 120 equals 4. And when I make it into that equation with that equals 4, I can interpret that entire thing. The g first tells me the day 2 part. The 120 tells me 120 is the input. So that means we're talking about 120 seconds. And then the 4 is actually telling me what that distance would be. So G of 120 equals 4 would mean on day 2, 120 seconds after the dog owner left, the dog was 4 feet from the post. It's similar to what we were doing up here, but now we actually can say what that distance was. We can say how many feet it was away from the post. And so similar to this one here, I've got 3 for you to try. Use this part up here. Oh, where's my highlighter? There it is. Use this part up here as an example to help you come up with these 3 equations for what they would represent. Once again, go ahead, pause that video and see if you can do that now. And you're back, and I have some answers for you. This first one, the H tells me we're talking about day 3. So I could start by saying on day 3. The 40, my input is always the time. So that 40 is telling me we're talking about 40 seconds after the dog owner left. So similar to what we were doing up here, except now that equals 4.6 is telling me that exact distance. So I could finish this by saying the dog was 4.6 feet from the post. These other 2 here are really similar. It's just we've got missing information now. This one here, it has an F, so that tells me we're talking about on day 1. But because that input is missing, it means I don't know the time. So we could say T seconds after the dog owner left. The 5, though, I do know that's my output. I do know that's my distance. So I could say on day 1, T seconds after the dog owner left, the dog was 5 feet from the post. So maybe I wanted to give that to you and ask you to figure out what time is that. If we looked at that graph on day 1, could you figure out the time where the dog was 5 feet from the post? I could give that to you as a question and ask you on this graph to kind of figure it out. Similar to what you were doing in number 1, right? There's one last one down there, G of T equals D. This one now, there's no numbers, but you can still write a phrase to describe this. The G tells me we're talking about on day 2. The T tells me I don't know how many seconds, but I know it's seconds still. So T seconds after the dog owner left. And D, again, I don't know what the number is, but I know that D represents the distance. So I could say on day 2, T seconds after the dog owner left, the dog was D feet from the post. I know we said it yesterday with function language, and learning a language isn't something that happens in a day. And this is kind of like a new language, right? Representing these functions in this new way. And it's not something we're going to learn in a day. We're going to practice function notation in pretty much every lesson in this unit. But a quick summary of what we're seeing here with function notation is when you're given something like this, that variable or that letter outside the parentheses, that's representing the name of the function. So here, because we were talking about 3 different days, we had 3 different names for these function relationships. What goes inside is your input of your function. So whatever is in those parentheses, that's always going to be the input in the relationship. And then together, all of this represents the output. So they've got the bracket around the f of t. All of that represents the output, which here was the distance. So you could see it that way, or you could also see it as f of t equals d, where your distance or your output comes after that equal sign. So at this point, we've introduced this idea of function notation. Like I said, we're going to keep practicing it this whole unit. We do have one last opportunity to practice it down here, where we're going to talk about birthdays. And so in this last part here, there are 2 rules that are going to describe the way we fill in this table. Rule B, this first one, takes the person's name as its input, and it gives their birthday as the output. So kind of think of it like Google. I'm typing in the person's name, and out comes the person's birthday. So for example, you put in Abraham Lincoln, and the output, the birthday, is February 12th. I could put in my name, Samantha Griffith, and out comes my birthday. Nope, that's not my birthday. Out comes my birthday of May 27th. Another example, I know Martin's birthday. Martin Bruner's birthday is January 25th. Or, of course, we could put you in. So you could put your name into the table, and then the output would be whatever your birthday is. That's how this first one here works. The second rule is similar, but it works in a different order. So for the second one here, rule P takes a date as the input and gives a person with that birthday as the output. So for example, if you put in the date August 26, Katherine Johnson, who is a famous female mathematician who worked for NASA, out comes her name. And we could keep doing this. So maybe I put in my birthday and possibly my name comes out because it is my birthday, right? Or we could put in your birthday, right? And maybe your name comes out. For one other example, I know Mariah's birthday. I know her birthday is February 3rd. So maybe you put in her birthday and guess what? Out comes Mariah's name. So that's how those 2 rules work. So we've already done the first part, which is completing those tables with 3 more examples. But I want to consider these 2 relationships and the idea of how many outputs are possible. So thinking about this first table here, this rule B, if you were to use your name as the input to B, so we put in your name, how many outputs would be possible? How many different dates could come out of that table? Take a moment to think about that. Well, if you put in your name, there should be only one output coming out. You only have one birthday, right? So here, there's only one output. And that explain how you know you only have one birthday. If I took your name and put it in, the only thing that should be coming out is that one date that's your birthday. Just like for me, right? If I put in my name, I only have one birthday, so only one date is going to show up. What about with rule P? If you put in your birthday as the input, how many outputs are going to be possible there? Now, these might seem like the same question, but they're different because here it's reversed. I'm actually going to use Mariah as an example. We put her birthday, February 3rd, in, and a possibility would be getting her name. But I used Mariah because if you know Mariah, you might know that she is a twin, which means she has a sister on the same birthday. So for that February 3rd, maybe her name comes out or maybe her sister's name comes out because they're born on the same day. And guess what? Mariah and her sister are not the only two people born on February 3rd. Maybe you're watching this and your birthday is February 3rd. But the point is, there is a lot of people who share that birthday. I put in for me May 27th and out came my name, but there's a lot of people who are born on May 27th. So it might be my name here, but it could be other names. So that question of how many outputs are possible, there are a lot of possible outputs. And sometimes we like to use that word infinite. There are infinitely many outputs. For why? Because there are a lot of people who share the same birthday. I am not the only human being on earth who was born on May 27th. So keeping in mind this idea of how many outputs each of these relationships have, I'm going to tell you only one of these two relationships is a function and the other one's not a function. Can you figure out which one is which? If you feel like you can, go ahead, pause the video now. If you feel like you need a clue, my clue is up at the top. We started off this lesson by visiting this idea we had talked about yesterday. We introduced this definition of a function yesterday, and that's going to be the important part for this question. If I can go away, there it is. Our definition of function yesterday was a relationship where each input has only one output. You're going to need that information and that definition to help you with this last part. So coming back to our question, think through number 4. Which one of these is going to be the function? We said a function is a relationship where each input has only one output. And so we said it was this first one here, B, that had only one output. So our answer is this first one here. This is the function. It is a function because each of these inputs has only one output. This one here is not a function. And if I asked you to explain why it's not a function, it's not a function because one input, we said, could have many, many, many outputs. And so this last part here is, now that we know this first table here is a function, if it's a function, that means we can use function notation with it. So function notation was this fun thing we introduced here. Up here, we were using numbers with it, which is the most common way you're going to see it. But you can also use words with function notation. So this last part here is for that relationship that was a function. Let's write 2 of those pairs of information using function notation. So you could take any of these names here, you could do it yourself. See if you could write it using function notation from earlier. Go ahead, pause the video and try now. Remember from the first part, we said in order to use function notation, there's 2 or 3 key things we're looking for. The first thing I need the function name. And so it was already named for us. It was named with the letter B. So when I go to start my function notation, I'm going to put down the letter B. And then I'm going to have some parentheses. Do you remember what goes in parentheses? What goes inside is always going to be your input. So for example, if I wanted to do Abraham Lincoln, my input, his name, is going to go in those parentheses. So inside those parentheses, I'm going to write Abraham Lincoln. And we get B of Abraham Lincoln. And for this last part here, because I know what the output is, I can write equals and then our output. Our output was his birthday, February 12th. February 12th there. You can go ahead and try to represent some of these other ones using function notation. I don't know your birthday, so I can't write it for you. But for example, I would be B of Samantha Griffith, and then equals the output, which is my birthday, May 27th. For you, your name would just be where my name was, and then your birth date would be after that equal sign there. Like we said, the goal of this lesson was to practice 2 things this idea of being able to represent these situations with function notation, and the opposite, look at function notation, like these statements right here, and understand what they mean. So I think this page here is a good summary of what we were trying to do. We're taking this description in words and using function notation to represent it, or we're taking function notation and understanding what words we could use to describe the function notation. I feel like I said function notation a lot. A great way for you to check and see where you're doing it on this concept is this cool down here at the end. It goes back to that warm-up we had done yesterday with the bagels, where we were talking about how many bagels you were buying and then the best price for those bagels. So for that cool down, we've got the best price for bagels in dollars is a function of the number of bagels bought, which we're going to use N to represent that. There are 4 statements right here. See if you can read each of these and interpret those statements that are written in function notation. One last time, go ahead, pause the video now, and try this cool down. All right. So thinking about the scenario from yesterday, one of the things we had identified yesterday was the input in this scenario was the number of bagels that you purchased, and then the output was that best price, best price for all those bagels you purchased. Knowing that's important because for these first 2, I know whatever's in my parentheses is going to be my input. And so looking at this, I know the 2 and the 6 are both describing the input, which is the number of bagels. That means B of 2 is going to represent the best price of 2 bagels, and B of 6 is going to represent the best price of 6 bagels. These other 2 right here that are equations are telling me a little more. So similar to these first 2, B of 11 equals 1050. The B of 11 part tells me we're talking about the best price of 11 bagels. But to finish it up now, I can actually say what that best price is. The best price of 11 bagels is, and then I know that 1050 must be the best price. So I could say the best price of 11 bagels is $10.50. For that other one, B of 13 equals 11.25. You have this one right. B of 13 means I'm talking about the best price of 13 bagels. And that equals 11.25 tells me I can actually say what the best price is. The best price must be $11.25. We are going to continue to practice function notation in the upcoming lessons, but being able to do this and not just be able to write it in words, but also write it in function notation is going to be an important skill in this unit that we're going to keep practicing. Hopefully you found this video helpful. Thanks so much for watching, and I will see you tomorrow. Bye, guys.